Hi, my name is Dibya Ghosh. I'll be talking about representations for stable off-policy RL. This is joint work with Marc Bellemare. If we step back and look at value-based deep RL, we can see three core components. We use function approximation, in particular deep neural networks. We use off-policy data through our replay buffers, and we use temporal difference learning to learn these value functions. Now, deep RL has been successful, but there have been many challenges on the way of stability and of optimization. And this is something we've known for a long time, that when we combine these three components, function approximation, off-policy learning, and bootstrapping, the deadly triad, so to speak, there are no guarantees of convergence. And in fact, in many cases, as a famous example from Baird shows on the right, the parameters can even diverge to infinity. It's a fundamental issue in RL theory, and it happens even in the most basic setting, with policy evaluation and with linear function approximation. Now, in deep RL, we've developed many empirical band-aids to reduce the problem of instability in practice. One particularly successful path has been to use representation learning. In addition to learning just the value function, we add auxiliary objectives, such as predicting future observations or predicting future rewards. These auxiliary objectives shape the representation that is learned by the neural network, and in practice is known to stabilize training. Now, this is a wholly empirical observation, but it leads us to ask, can representation learning be a path to provably guarantee stability of off-policy RL? In this work, we formally study the problem of off-policy divergence through the lens of the state representation. Through this presentation, we'll encounter three big insights. Stability, when using a particular state representation, depends not only on what value functions we can express, but also how these value functions end up being represented. We'll find that some representation learning procedures always create representations that induce stable learning. These representations are in some sense consistent with the dynamics of the environment. And towards deep RL, we'll show that there are simple auxiliary tasks that can learn stable representations when using neural networks. As a whole, this work is a step towards understanding how we can use representation learning as a tool towards stabilizing off-policy RL. Now, the main object of study in our paper is a simplified setting, policy evaluation with linear function approximation. In policy evaluation, the goal is to learn a state action value function, Q, that estimates the future return of some policy, pi. We're going to optimize this Q function using transitions that are sampled from some data distribution. This data is not necessarily collected from the policy that we're trying to evaluate, and hence the algorithm is off policy. Our Q function will use linear function approximation, and these features, phi of SA, are what we call the representation. So as we can see, we have all three components of the deadly triad in our setting: off-policy data, function approximation, and bootstrapping. The canonical algorithm for learning the value function, which we study, is TD0. It follows the update rule listed here. The update weights the gradient of the Q value at a particular state, the first term, by the TD error at that state, which is the second term. This update is known to be unstable under the deadly triad. But we'll call an update stable if for some step size, the parameters converge from any starting point. Stability can be studied by looking at the learning dynamics as the step size goes to 0. In this limit, TD0 follows a linear dynamical system, where the matrix A determines the stability of the update. Now, at a high level, this matrix A is a function of three things: the environment dynamics, the representation, and the data distribution. Now, depending on how these three things are chosen and how they interact, the TD0 update will either be stable or unstable. Now, with this setup in place, let's come to the goal of the work, which is to determine how the choice of a state representation can affect the stability of TD0. we're going to call a representation a stable representation if TD0 in an MDP is stable when we use this representation. The general blueprint for representation learning will go as follows. We're going to be given access to an environment, typically using samples from our data distribution, and we're going to use some representation learning procedure, such as proto-value functions or the successor representation, to learn a representation phi. Having learned a representation, we're going to judge whether or not TD0 is stable using this representation. Now we'll find that some representation learning procedures may always create stable representations, others only sometimes, and others even still may never create stable representations. Our first important discovery through our analysis is that how a representation is parameterized can actually affect stability. We can have two representations that express exactly the same set of value functions, but where one diverges and is unstable, whereas the other one is stable. This picture shows an example where all three representations, blue, green, and red, all represent exactly the same space of value functions. They're equally expressive, but the red representation is unstable, whereas the other two are not. There's an important exception to this rule that we study further. Representations that are normalized and uncorrelated. We call these orthogonal representations. For these representations, stability depends only on the projection map. Basically, TD0 using an orthogonal representation can be thought of as replacing the true transition matrix dynamics using what we call an induced representation matrix, which views the environment transitions through the lens of our representation. Stability of the representation depends on how well the induced transition matrix preserves the eigenvalues of the original transition matrix. Now, with these ideas in place, we'll now illustrate some fundamentals of stability by doing a case study of several previously proposed representation learning algorithms. These representations are based on PVFs, a representation that captures the global structure of the environment. Now, the original PVF is actually impractical to implement, but several methods have generalized the idea to be able to learn in arbitrary environments. Under on-policy data, in a symmetric environment, these methods are all the same. They all create proto-value functions. But when using off-policy data, these methods generalize in different ways. And depending on how they choose to learn under off-policy data, some always create stable representations, whereas others do not. The first two choices of representation, the SVD and the successor representation SVD, minimizes the reconstruction error with the transition matrix. Now, by focusing exclusively on reconstruction error, the eigenvalues are left uncontrolled, and the induced transition matrix does not preserve the eigenvalues of the transition matrix as needed for stability. Moving forward to the Laplacian, some of the features of this Laplacian we find to grow unsafely. These are features whose values grow on average above a certain amount from the current state to the next state. And if a representation is comprised only of these growing features, we find that the parameters will grow larger and larger, ultimately diverging to infinity. Now, there's a simple solution here, which is to just omit all such high growth features. This leads to the safe Laplacian method, which is always stable. Now, this is one example of a class of representations that we analyze. We call these positive definite representations. These representations achieve stability by reducing expressiveness in directions of unsafely high growth, trading off expressiveness for stability. The final representation on our list is the Schur representation, which finds features that are invariant under the transition dynamics. That is, the feature values at the current time step are predictive of the feature values at the next time step. This representation is optimized specifically to preserve the eigenvalues of the transition matrix and is therefore always stable. The Schur representation is an example of another class of representations we study, which we call approximately invariant representations. These representations are stable and expressive, and stability under this class is a consequence of the representation being consistent through time. That is, future values at one time step are able to predict future values at the next. With the main principles for stability using representation learning set, let's now consider how we can learn these representations using deep learning. In the last part of this talk, we'll show that the stable Schur representation can actually be learned using a deep neural network by optimizing a very simple auxiliary task objective. Now, without function approximation, the Schur representation is learned via a linear algebra procedure called orthogonal iteration. At each step, we fully solve an optimization problem, choosing a representation phi that is most predictive of our current representation at the next time step. When we add neural networks, a couple things change. Phi is now a neural network, and we can't exactly find the argmin of this objective. So instead, we're going to use gradient descent to optimize this loss function for a sufficient number of steps. And once we're close enough to finding the argmin, we'll go to the next stage of the iteration. To put this into deep RL terminology, we have the following loss function, where phi bar is a target network that is updated every L steps. Now, while the target network is fixed, we're trying to find an approximate solution to the argmin problem listed above. And every time that the target network gets updated, it corresponds to moving to the next step of orthogonal iteration. Let's actually look at this loss function a little more visually. We're going to feed the current state into our representation phi. This is what we're optimizing for. Now, we're going to feed the next state into the target representation network, phi bar. And what we're going to do is we're going to add a linear layer, M, on top of our representation. And we're going to optimize both M and our representation phi to try to predict these next state future values. Now, when we see it like this, it's very clear that the Schur representation actually corresponds to the simple auxiliary task of predicting the features at the next time step. As a didactic example, we train a neural network with this objective on the 4 rooms domain. Now, notice that the loss function is periodic. It decreases while the target network is fixed and we're solving our argmin problem, and it spikes again when the target network gets updated and we move to the next step of orthogonal iteration. On the right, we measure a quantity that we call invariance of a representation. Our theory says that when this number is appropriately low, the representation is stable. And we find that indeed, with our neural network, the representation eventually becomes stable with enough training. Now, this is obviously a simple example, but it shows that in principle, neural networks using this type of auxiliary loss can learn stable representations. To summarize, in this work, we provided a formal analysis of how representation learning can affect the stability of off-policy RL. We found general principles for what makes a representation stable, and we found that these representations can actually be learned using simple auxiliary tasks. There are 2 exciting future directions I'd like to highlight at this point. First, how can we formalize learning dynamics when we're learning the value function and representation concurrently? And second, extending these ideas of stability to the control setting. If you have any questions about our work, or if you're interested in learning more technical detail, please check out our paper and join us at the poster session. Thank you.